Okay, good morning. So let us start today's lesson. So I want to continue a little bit about this notion of divisibility in number theory. So remember, I talked about number theory. I told that this is an active branch in mathematics. And then mainly number theory deals with the set of integer numbers and its subset, which is the set of natural numbers. Okay, and then the first notion that we defined in number theory, which actually you are very familiar with even from primary school, but we put it in a more formal footing. So I told you that if we have two numbers, A and B, in the set of integers, and then we have this symbol that we say B is divisible by A, which was the usual way of reading this, but from now on I will mostly read it in this way: A divides B, yes? So A divides B means that B is divisible by A. This happens, we say that A divides B is equivalent to saying that there exists a Q in the set of integers, which is very important, such that the right-hand side is equal to the left-hand side multiplied by that Q. If I can find such an integer with that property, then I would say the left-hand side divides the right-hand side. Yes? And of course, mainly, intuitively, if you want to understand it immediately, this means that if I divide B by A, I get an integer. So if you want to do it quickly in your head, so this is the way that we do it. We divide the right-hand side by the left-hand side. If it happens to be an integer, then we say that the left-hand side divides B, or B is divisible. Yes? Of course, there are some exceptions that this definition will work. For example, here in this case, if we accept this as our definition, then this statement will become true. Even though in that case, if you want to use your intuitive idea to divide 0 by 0 to see if this is an integer or not, this will not work in this case because 0 divided by 0 is not defined at all, yes? But if I ask you, is this a true statement or a false statement, you would say that if I accept this as my definition, then 0 divides 0 is also a true statement. Why? Because the right-hand side is 0, the left-hand side is 0. Can I find any integer so that when I multiply it by this, it becomes this? Of course, we can have infinitely many integers as well here. So for example, any number that I want will work here. So for example, instead of Q, I, for example, can write 2. Is this a true statement or a false statement? Clearly, it's a true statement because 0 times 2 is indeed equal to 0. And then if I ask you, is this 2 an integer, you would say yes. So because this satisfies this condition, then if I consider this as my definition, this statement would be true. Yes? But for example, what about this statement? Is this statement true or false? This actually is very intuitive, yes? In the natural way, you divide 2 by 0, you realize that this is not possible. So you might think that this is false, and indeed you are right, yes? Why is this false? Because if this is going to be true, then it means that I should be able to find a Q in the set of integers so that when I multiply it by the left-hand side, it becomes the right-hand side. But this is impossible, yes? Because whatever I choose for Q, when I multiply it by 0, it becomes 0 and it cannot be equal to 2. So you see, I would say that the idea that A divides B, in your head, you can divide B by A, and if it turns out to be an integer or Hiltal, then you would say that yes, this is true. The only exception might be is this exception. Yes. So I would say that almost always it works. So if you want to do it quickly in your head, you cannot understand it in that. Is that clear? So that was actually a little bit of recap what we learned the previous time. And I would say that it might be better if we do some exercises today regarding this to see how it goes. So let me ask you one question. For example, let me write an example. Now, from now on, I will consider that the numbers that I am dealing with are not zero, to not to be worried about this special case. Yes. So I would say that let A, B, C, and D be non-zero integers. Such that we know that A divides B and C divides D. Show that if I multiply A by C, it becomes a new number which will definitely divide if I do B by D. So I want to show that if A divides B and simultaneously C divides D, then the product of A and C definitely will divide the product of B and D. I hope that this is very, very clear for you, even without formal writing, yes? Because I told you that, what does this mean in your head? It means B over A is an integer, yes? And then what does this mean? It means that B over C is an integer. If I have one integer here and one integer there, I hope that you agree with me that if I multiply them, the product is still an integer, yes? But when I multiply them, what happens? The numerators will be multiplied together, the denominators will be multiplied together. So this means that this fraction is an integer. When this fraction is an integer, it means that its numerator should be divisible by its denominator. And this means that AC divides BD, yes? So it's very, very clear intuitively, but if you want to write it formal, I want you to learn how to write formal things in mathematics at the level of Math 5. Okay, so what should I do? Let me change my color. So I would say that when you tell me that A divides B, according to my definition, I am allowed to conclude that there exists a Q which belongs to Z, such that the right-hand side is the left-hand side multiplied by that number Q, yes? When you tell me that A divides B, I am allowed to conclude this based on the definition. And then when you tell me that C also divides D, what can I conclude? I can conclude there exists a Q in Z such that D is equal to CQ. Is that understandable? But there is a small flaw in the second line. What is that? This is something standard in algebra. If I use two variables, x and y, for example, if I solve this system of equations, if I solve this system of equation, you can immediately guess what is x and y here. X is 1, y is 1. Yes, x and y are both the same numbers, even though I am using different letters for them. Because this is a common convention in algebra. So if you use two different variables, two names for different variables, it doesn't necessarily mean that they are distinct. They might be the same, yes? But if I use the same letter everywhere in the problem that I'm solving, I'm forcing that x to be the same all the way until the problem is finished, yes? So when I say that there exists a Q in Z, and I would say there exists a Q in Z with that property and that property, in this way of writing, I am forcing this Q to be the same Q that I am using here. But there is no guarantee for that to happen, yes? For example, if I say 2 divides 6, what is the Q here? Q here is 3. When I say that 4 divides 8, the Q here is not that Q. It's what? It's 2 in this case. So the same Q, I cannot use it for 3 and 2. Yes? So I have to change the name to something else. And so that's very, very important. Be careful. Of course, at the end, it might happen that the Q's are the same, but if I write the same Q, it means that I am forcing them, or there is some guarantee that these two Q's are the same, which I don't have that guarantee, yes? When I don't have that guarantee, I should change the name of the letter. Or I can say Q, I can say T, but usually let me put a prime here. And this prime doesn't mean at all. It's not related to derivative at all. I'm just changing the name of my variable from something to something else, yes? Is that understandable? So then I have to change this one as well. So that is very crucial. If you have different Q's, if you don't have any guarantee that those Q's are the same, you are not allowed to use the same letter to denote them, unless you really know that they have to be the same. Yes, is that clear? So if you write Q, technically it is not correct. Yes? Okay, now look here. What I want to have AC and I want to have BD. This will motivate me to do something with these two equalities, because the rules of equalities we know a lot about, yes? By the way, this is a relation between these two numbers. This is also a relation between these two numbers. But which relation is more familiar to us? Of course, equality is more familiar to us. So what we are doing, we are changing a relation which is not that familiar to us to a relation which is more familiar to us, and we know more rules about that, so we can use the rules that we have learned so far to do and find something about this new relation. Yes? So that's the idea. Okay, so if I know that two numbers are the same, two pairs of numbers are the same, am I allowed to multiply them side by side and conclude that the products are also the same? Very simple property of equality. If I give you that this pair of numbers are equal, and I give you that this pair of numbers are also equal, if you want to, you can conclude A times C and B times D are also equal. Yes? That's one property of equality. So I can use that property here, and I multiplied it. What was my motivation to use this particular property of equality? So because I see that what I'm looking ahead of I see that I need AC and I need BD. So this motivates me to multiply them, yes? But let us see if it works or not. So I multiply this by that. If I want to keep this equality, I have to multiply the right-hand sides as well. Yes? But then I hope that you understand what is going on. I have to reorder them a little bit, regroup them. So I write A and C together, and I multiply Q and Q prime together. Yes? But now you are telling me that Q is an integer. You are also telling me that Q prime is an integer. So what can I conclude the product? Is the product also an integer? Yes, because both of them are integers. So this also belongs to the set of integers. Yes, definitely. This is crucial. So this means that let me call it a capital Q. But I know that this capital Q is an integer. That is the crucial part. So now what is happening? AC, which is a number, multiplied by an integer is equal to BD. What can I conclude from this equality? I can conclude the number on the right divides the number on the left. Yes, is that understandable? So this is actually the same thing. It's not different at all. But I want to write it in a little bit more formal language. Is that understandable? Yes or no? Okay. What do you think about this? Do you think I can also conclude this? So inequalities, do you think I can conclude this as well? A plus C is equal to B plus D. Do you think that I can conclude this one as well if I give you these two? Yes, for equalities I can also add side by side. Yes? But what do you think? Do you think that I can also add this relation side by side and conclude that A plus C divides B plus D? So you see, this property is similar to the property of equality. But now this might motivate, this might be a natural question if you are interested in these things. So you would say that, okay, I had this property from equalities. Let us discover if the same property also holds for this new relation. Yes? So whenever you learn something new, mathematics, you need to play around with that concept to understand and to extract information as many information as you can get. Yes. Okay. So now, what do you think? Do you think this is also true? If that is true, you need to prove it formally. If you have a hunch that this might not be true, then you need to provide me a counterexample. A counterexample means that you need to give me 4 numbers so that this is right, but this is false. In that case, I believe that no, this is not a reliable rule. Okay? So, do you think it's true or false? If true, you have to prove it. If false, you have to refute it. Okay. So let us go back here. You see, that was very, very crucial not to write Q prime. No, not to write Q, but Q prime. Because if you mistakenly had written Q, then you add them, what will happen? On the right-hand side, you will have IQ. On the other side, you will have CQ again, if you had made that mistake. And then what happens? You can write A plus C and then factor a Q out. Yes? And then you would say that an integer multiplied by this is this. And then you will conclude that A plus C divides B plus D, and then you will try to sell this as the proof of that to me. Yes? But I will not buy it. Yes? Do you understand that? So this was very, very crucial. If you have mistakenly written Q instead of Q prime, that was the proof for this, but this is false. Is that clear? Yes or no? Okay, so now why this is false, could you come up with your example? Yeah, try to make a very simple example. Yes?
1 divides 2 and 2 divides 6.
And 2 divides 6. So let us say, is this true? Yes. Is this true? Yes. So now, is it true that 1 plus 2 divides 2 plus 6? Which is false, yes? Because 1 plus 2 is 3, 2 plus 6 is 8, but that's false. So this was true, but this was false. So this means that this is indeed not correct. So it was very crucial to see that how much difference is that if you put that little dash on top, then something which was, if you didn't do that, something which was wrong, you were able to prove it, but which is not correct, okay? Okay, so you see that this is different. This property of equality is true for this divisibility relation, but this property of equality is no longer true for divisibility relation. Yes? Is that clear? Yeah. So what we are doing, we are just playing around with this concept so that you can get used to it. Whenever you learn something new, you have to work around that so that you fully understand what's going on. Okay, so now let us go and ask you to do another problem. Okay, so do you remember, at some point I talked about whenever a relation comes in, then there are 3 words that might be, let us repeat them even though they are not in the book. So a relation could be reflexive. Yes, a relation could be symmetric. A relation could be transitive. Okay, so these are 3 words. Might be useful if you are interested in mathematics. Yeah, it's not bad to know these words. So we say that a relation is reflexive if every member has that relation with itself. For example, let us consider equality. Equality is a relation between numbers, yes? This is reflexive. Why? Because every number is equal to itself. Yes? Is that clear? So that is reflexive. So for example, this relation in numbers, is it reflexive or not? No, because if I write 1 smaller than 1, this is a false statement. So 1 is not related to 1 by this relation. Yes? But 1 equals to 1 is true. So it means that 1 is related to itself by this relation. Not only 1, any number is related to itself by this relation. So this means that equality relation is reflexive. Yes? Yes or no? And then symmetric, it is clear from the name. Symmetric means that if A is in relation with B, then you can conclude B is also in relation with A. Yes, which is completely true for this case. But again, do you think this is reflexive? Sorry, this is symmetric? No, because if 1 is smaller than 2, which is true, I cannot conclude that 2 is also less than 1. So this relation is not symmetric. It is sensitive if I interchange the numbers. Okay. But what is the meaning of transitive? Transitive means that if I have A in relation, let me use equality here. This is one of the relations. If A is in relation with B and B itself is in relation with another number, can I conclude the first one and the third one have the same relation? Yes. Yes. So that is true. So this means that equality relation is transitive. Yes? So do you think that this relation is transitive? Yes?
It should be.
It should be, yes. Because if A is less than B, and you tell me that B itself is in relation with the third number, can I conclude the first one and the third one have the same relation? Yes, you say that definitely A is less than C. Yes? Yes or no? Okay. What do you think about this relation? Let us discover the properties of this relation, divisibility. So do you think that this is reflexive? Reflexive in this question means that is it true that every integer is in relation with itself using this relation? Is it true or false? So in principle, let us choose A in Z, whatever you want to. You need to answer this question. Is this true that A divides itself for every number? Yes, even 0. Yes, do you remember we just started today that 0 divides 0 is also true. So we will say this relation is reflexive. But do you think it is symmetric? Symmetric means so it was true. So it is reflexive. Is it symmetric? Symmetric means that if A divides B, can I necessarily conclude that B also divides A? If the answer to this for all choices of A and B is yes, then I would say that this relation is also symmetric. But is that symmetric? No, it's very clear that we can make a lot of examples, yes? We can say 2 divides 6, but is that true that I can conclude that 6 also divides 2, so which is wrong? So it is not symmetric, yes? It's reflexive, but it is not symmetric. But what do you think? Do you think it is transitive? So that is my question. You want to answer that question. It's not hard, but I want you to know these things. Do you think it is transitive or not? So what does it mean? If I want to translate this question, so let me write a title for the question. So example, is divisibility relation a transitive relation on the set of integers this is a little. So this is a sentence, English sentence, but you can immediately, if you understood what I mean by the word transitive relation, then you can translate it in a very simple language. So how should I? So what is your hunch? Is it yes or no? If you say no, you need to give a counterexample for me. If you say yes, you need to write it and prove it for me. Yes?
Yes.
The answer is yes. So how do you think about this problem? So you ask yourself that if I have three numbers A, B, and C, if you tell me A divides B and simultaneously B divides C, Amanda is claiming that this is transitive, so it means that we should be able to conclude that A also divides C. Yes, so that is what you mean. So if that is the case, we have to prove it. Yes, so how should I prove it? So I will start from this. I would say that when you tell me that A divides B, I can immediately conclude that there exists a Q in Z such that the right-hand side is A times the left-hand side. The left-hand side times Q. And then you are telling me that at the same time, B itself divides C, so I can conclude there exists a Q, but not necessarily the same Q. So let me change it to Q prime belongs to Z, such that what happens, the right-hand side is the left-hand side multiplied by that Q prime. Yes? So if you guarantee these two, according to the definition, you have to admit that these things are also true. But then my question is somehow I want to relate A and C without any track of B. So I need to get rid of B, in other words. So what should I do? It's very easy, yes? I have an equality here, but I know that B itself is equal to that one. So it means that if I want to, I can replace this B with AQ, because they are the same. So I would write C is equal to, instead of B, I write AQ, and instead of Q prime, I just simply put Q prime. But you need to use associativity of products, so I can just regroup them. And then the important thing is that you have to make sure that this is guaranteed to be an integer. It is, yes, because Q and Q prime are in Z, so the product is an integer. So this means that if I want to, I can give it a name Q, and I make sure, of course, I always can give it a name Q, but the point is that in the number theory, this Q should be in Z so that I can conclude this divisibility relation. So this means that A multiplied by an integer is equal to C. So what can I conclude? I can conclude that A divides C. Yes? Is that clear? Okay. So it's very, very important. I recommend you to remember this fact. If A divides B, B divides C, A also divides C. Okay, so what do you think about this? What do you think about this? If you tell me that A divides B, of course A and B are integers, and then you tell me that n is a natural number, do you think I can raise both sides to some power n and conclude that this is also true? So this is also another relation that you might think. In equality, if I know that two numbers are equal, definitely I can conclude that A to the n and B to the n are also equal. So because of this property, I might be interested to answer the same sort of question for this new relation. Yes? Do you think this is true or false? First of all, do you tell me why do I emphasize that n should be a natural number here? Yes? I told you that A and B are in Z, but I am restricting myself for n to the set of natural numbers. Yes?
It will not be an integer.
Yes, if it is a negative value, then a to the power of negative value, it becomes a fraction, and a fraction is not an integer. I am only allowed to use this relation among the integers, so that would be nonsense, yes? So, what do you think? Do you think it's true or false? Yeah, true or false? Yes? Yeah, it is true, yes? So how should I prove it? I would say that you tell me that A divides B, so I can conclude that there exists a Q in Z such that the right-hand side is equal to the left-hand side multiplied by that Q, because I want to relate these together. So this motivates me to raise both sides to power n, which I can do it, yes, because I know the rules for equalities. If two numbers are the same, definitely the nth power of the left is equal to the nth power of the right, yes? And this is clear. And then if I can continue, we know that if I have a product, I want to raise it to power n, I raise the first one to power n, I raise the second one to power n. But do you think that I can conclude that an divides bn? Can I conclude from here this one? Yes or no? Yeah, just be quick. Yeah, the answer is yes. Why? If I insist to ask you why, how do you answer? To come to this, you need to make sure of one thing. What is that one thing? You need to make sure this is an integer. Yes, if this is not an integer, or there is no guarantee that this is an integer, then you are not allowed to conclude this. But if you're sure that this number is an integer, you are allowed to go back and you are allowed to go forward. Yes. So is this an integer? Yes, because you are guaranteeing that q is an integer. You are telling me that n is a natural number, so I am raising an integer to a natural number. So definitely it is an integer. Yes. So this is crucial because this guarantees that this is an integer. I can conclude that. Yes. So that's also good to know. If you want to, you can raise both sides to some powers. But now let me ask you one more question. Do you think that I can raise inequality? So if I have A equals to B, do you think I can conclude that A2 is equal to B3? So if I guarantee that two numbers are the same, is it also guaranteed that A squared is equal to B cubed? This is not guaranteed, even though it might be true, yes? If this is 1 equals to 1, then 1 to power 2 is equal to 1 to power 3, but that's an exception. In general, we cannot conclude that. But what do you think about this relation? So you remember we had some relations for equality, some rules for equality, which was not working here, but now I want to show you that there are some rules for this relation that is not valid for equalities, yes? And then what I am trying to say is that, what do you think? If I tell you that A divides B, can you conclude that? Let us just be a little bit special. Do you think that I can conclude this? Or do you think that I can conclude this? Is there any one of them which is true or not? Yes? The one above is true, yes. But the one below might not be true. Yeah, so that's good. So you see, this was not true if this relation was equality. Okay? But this is true when this relation is divisibility. So I am allowed to raise both sides to powers as soon as I keep the right-hand side power equal or higher than the left-hand side power. Then that is true. And that's very clear. Why? Let me just try to prove this one for you. So how should we prove that? Let me consider that this is true, and we want to show that yes, this is indeed true. You are telling me that A divides B, so I can translate it as the definition of that. So I would say that when you tell me that A divides B, I am free to conclude that there exists a Q in Z such that the right-hand side is A times Q. Okay, but can you tell me how should I proceed and try to prove A squared divides B cubed? By the way, intuitively, it should be a matter of seconds for you to understand this is correct, because I told you that when you say that A divides B in your head, it means B over A is a whole number, is an integer, yes? But now you want to divide B3 over A squared. But B3 over A squared can be written as B over A in your head, multiplied by another B over A, multiplied by an extra B. Yes or no? So then what happens? You are telling me that this part is an integer because of this assumption. So that is an integer according to your assumption. This is the same number, so that's also an integer. But I start with integer B. So integer, integer, integer. So if I multiply them, that becomes an integer. Yes, so definitely this is true. So in this way, you can immediately understand that without going into much detail. So this is very important to have this in your head. Okay, now can you tell me how should I solve this problem formally? I need to raise both sides to some power, but which power do you think? Because there are two powers involved, 2 and 3. Which one will work here? On Mondays you're very sleepy, yes. You are warming up your brain or engine or something. Yes? So which power we should raise it to? Yeah, 3, yes? Yeah, we should raise it to power 3. So I raise it to power 3, so this becomes b to the power of 3, a to the power of 3, q to the power of 3. But the point is that, of course, I need b to the 3 by looking ahead, but I don't need a to the 3, I need a squared, but that is easy to solve, yes? Because instead of a cubed, I can write b to the power of 3 is equal to a squared, and I absorb one of those a's to q. That is important to understand. I don't care to make this number beautiful. I want to make sure that that number is an integer. That's it. Yes? Is that number an integer now? Q was an integer, so if I raise it to power 3, it's still an integer. And I started with a and b to be integers. So this combination is definitely an integer. Yes? So it means that now I have an integer multiplied by a square gives me b to the power of 3. So this means that if I want to, I can conclude that a squared divides b cubed. Yes? So that's the formal way of writing it, but that was intuitively very, very clear. It shouldn't take you so much to understand this from this point. Is that clear? Now, one question. Do you think this is also true? If a to the n divides b to the n, and if n is integer, of course, n is a natural number, do you think that I can conclude that these numbers without those powers also have the same relation with each other? Yes, yes. Otherwise it doesn't make sense to write. What do you think? True or false? You shouldn't be 100% right, but what is your hunch? Is it a true or a false? Yes?
Probably true.
Probably true. Okay, but let us try to prove it. There is something that I want to tell you. If I want to prove it using this method, where is my starting point? I have given you 3 numbers, fixed numbers, n, a, and b. A and b are an integer set, a set of integers, and n is a natural number. But they are fixed. Okay, now you are telling me that a to the n is dividing b to the n. What can I conclude? Can you write in front? What should I write in front of it? According to definition, what should I write? Just one of you, read it for me. Yes, there exists what? Q where? In Z, such that what? No, B no. The right hand side. Bn is equal to what? The left hand side multiplied by Q. Everyone agrees? So that's the translation of that. But you want to conclude something about A and B. Okay, so what is the natural motivation? What is the natural step to go forward? Because I have something between Bn and An. I want to write something between A and B. So what is the natural step to take? For example, take the nth root, yes? If I take the nth root of this one, it gives me B. If I take the nth root of this one, it gives me A. And if I take the nth root of that one, it gives me this. Okay, for the time being, you can consider that A, B, and are positive. Don't worry about these even and negative ones. Let us assume that everything is positive. And then I am telling you that A multiplied by a number is equal to B. Then I conclude that A divides B. Yes? Do you agree that this is a proof for this statement? Question mark? Yes or no? Yes? So what I did, I started from here. If you ask me why this is true, of course that is exactly the definition of this. So that's 100% right. Now, I was a little bit careless. If you are worried about negative signs and things, let us also consider that A and B are positive as well, so that I can make sure that I can take the nth root. I take the nth root of this one, definitely it becomes B. By the way, if this number is equal to this number, immediately it becomes clear that the nth root of this one should also be equal to the nth root of that one. So I'm not cheating at all. It's 100% right. And the nth root of B to the n is B. But this one, nth root of this part becomes A, but the nth root of this part becomes. So whatever I have written is completely right. And now I am saying that A multiplied by a number is equal to B. I conclude A divides B. Then I will try to sell this as the proof for that statement. The point is that do you buy it or not? And don't disappoint me. Yes? Do you buy it?
No.
Okay. Why? Yes. So that's very important, yes? So there is no guarantee that the nth root of Q is an integer. Everything is right up to the very last point. Yes? From here, I cannot conclude this. If I want to conclude this, it means that I am assuming that this is an integer. Yes? Otherwise, I cannot conclude that. But there is no guarantee that this is an integer. Because when you take nth root of an integer, there is no guarantee that that nth root is also an integer. It might happen. For example, you take the third root of 27, the answer becomes 3, which is an integer. But if you take the third root of 25, it's not an integer anymore. Is that understandable? So this means that this is not the valid argument. Yes? So the question is that, is it true or not? It doesn't mean that if I couldn't prove it in this way, this is false. Might be there is a more elegant way to prove it, and the answer to this is yes. There is a different way to show that this is indeed true. Okay? But we don't study that part. I don't know, factorizing the numbers to prime. So might be you can think in that way that is the case. But in the book we are not discussing that much about the properties of prime numbers, which is also a little bit strange because prime numbers is the building block of number theory. So in principle they have to pay more attention to the prime numbers. But if I want to teach all of those things, might be we'll not be able to finish what is in the book. So you can take my words for it. if a and b say natural numbers and n is also a natural number, from here we can also conclude that this is true, but this is not the proof. The proof is different. Yes?
Can you say that, for example, A divides B, so B divided by A, and then with parentheses to the power of n? For this to be an integer, B divided by A needs to be an integer.
No, that's the same thing.
But isn't that the proof?
No. So what we can repeat it again. So what you are saying? So you say that a n bn over an is an integer. And then you say that because of the rules of powers, I am guaranteed that b over a is an integer. But you cannot conclude that b over a is an integer.
But if it wasn't, then the whole thing would not be an integer at the end.
No, it might happen. That's the point. For example, the square root of 2 is not an integer, but when I raise it to power 2, it becomes 2. 2 is an integer. And that's exactly the same problem there. So this is just reformulating the problem in a different way, which is equivalent to that one. So this actually tells you this. If the nth power of a number is an integer, is it guaranteed that this number itself is also an integer? Which is not the case, yes? So this means that this is not the proof, but the proof is, there is another proof for this, which is actually working. So if you want to have it somewhere in your notebook, remember that this relation is also true. But the proof is not this one. At this level, I want you to understand, I shouldn't be able to sell this to you as the proof of this statement. This, if you understand that, we are done. That's my goal, yes? Is that clear? Yes. Okay. So now let me try to see what we can have more interesting here. So let me give you an example and wait to see how do you deal with that. Okay. So example. Let A, B, and C be non-zero integers. Such that, so we have this, A divides B and, oh sorry, let me write and usually. So, and B squared divides AC. Show that A divides C and B divides C. Okay, so I will pause the recording, so wait for you a little bit. Okay, could you solve the problem? Yes? So, yeah, I don't think it is very hard. I don't know how many of you could solve the problem. Yes, Ruben? Do you want to come and solve it here?
Yeah, sure.
Yes, please.
Okay, so A divides B means that there exists a Q that's an integer such that B equals AQ.
Yes.
And then the same for this one.
Yes.
So
No, write it. Don't be lazy. Okay. It's like again. Yes. B squared. Yeah, you need to write these things in the exam, by the way.
q prime.
Yes, yes.
And then this means that, and then I can multiply these. So b with ac and aq with b squared q.
Yes. So he multiplied both sides together, side by side,
Yeah.
yes.
And then I can reorder this, so it becomes ab squared times q times q prime.
Yes.
Like that.
So instead of arrow, you have to put equality
Oh,
on top, yes. So you use arrow when you want to go from one statement to another statement, yes?
oh wait. Yeah, I forgot BAC, so.
Okay, so then you need to put arrow.
So
Yes.
then it's okay.
Yes.
And then I divide by B
Yes.
and A,
A.
so it becomes C equals to B times Q prime.
Yes.
And then this is an integer,
Yes.
so that means I can write
Yes.
B divided C.
Yes. So that is one part of this story. So by this kind of argument, completely right. By the way, are you allowed to divide by A and B? Because you need to be careful. You are only allowed to divide when you are sure that that number that you are dividing the expression by is not zero. Yes? But this is guaranteed by the theorem itself that these numbers are non-zero. Yes? That's the reason that they have mentioned it shouldn't be non-zero. Okay.
And then I use this rule here. I don't know if I prove it, but AB
Yeah, very, very good actually.
BC.
Yes, yes, yes.
This means that.
Transitivity, yes?
Yeah.
Yeah, you are done. Thank you very much. Very nice. Thank you. Thank you very much. So, because you see that actually, so you proved this part only, and then combine this one with that one, and the transitivity to conclude the other one. Yes? So you really don't need to start proving the other one from scratch again. If you use transitivity and one part, you can immediately conclude the second one. Yes? But for example, I don't want to, this is the method that I want you to learn because I don't expect you to remember these rules so that you can use them effectively. But for example, if I want to solve that one, for example, I would say that A divides B, I can conclude that A squared divides B squared. This is that is what we learned. And then you are telling me that B squared divides AC. By transitivity, I can say A squared divides B squared divides AC. It means that A squared divides AC. Yes? And then I divide everything by A, so A divides C. So if you learn these tricks, but you need to remember them, and I don't expect you to remember them because that's not a very big part of your lesson. So as far as you can write this argument, that is enough. But if someone writes this one, that's also correct. Yes, that's very good. Okay, now let me make this problem ask you to, what is your opinion about this? So there are a few important things left here because next time I want to go to the next lesson. Okay. And this is what I want to ask. If I give you that a number, this is very important. A divides B and A also divides another number. I have one single number that I know divides two different probably numbers. I want to ask, do you think that the sum of these two numbers is also divisible by A? What do you think about the difference? What do you think about such a combination? Let me make it. So I know that two numbers are divisible by one single number. Do you think that the sum of those numbers is also divisible by that number? And I ask you the same question for the difference, or I ask you for this combination. Again, using that idea of b over a should be an integer is a good thing to immediately understand, at least if it is true or false. So let us concentrate on this question. I have one single number that divides two numbers. Is it guaranteed that the same number divides the sum as well? What is your suspicion here? Should it be true or false? It should be true, yes? Why? Because I told you that if you want to check it immediately in your head, you are telling me that A divides B. If I want to, what type of number is this? An integer, yes? Because you are telling me that A divides B. You are also telling me that A divides C, yes? So it means that C over A is also an integer. If this is an integer and this is an integer, what can I say about the sum of these two? The sum is definitely an integer, yes? But another way of writing this sum is what? Is to write B plus C over A. Do you agree? This number and that number are the same. So if this is an integer, this is also an integer. But if a fraction is an integer, it means that its numerator is divisible by its denominator. So the answer to the first question is yes. And what the answer to the second question? The same thing, yes? The only difference is that I will have a minus sign here, so then it becomes B minus C. The difference of two integers is also an integer, yes? So what happens? All of these answers are correct. So here, what can I see? 2b plus 5c, let me divide it in my head by a. Do you agree that I can write this combination as 2 times b over a plus 5 times c over a? Do you agree? I can write this in this form. But now you are telling me that b is divisible by a, so this is an integer. For the same reason, that is also an integer. Integer multiplied by 5, integer multiplied by 2, and the sum is also an integer. So the answer to all those questions is a yes. Yes? So let me write this in a general formula. So I would say that if a divides b and a also divides c, and m and n are integers, if you want to, you can conclude that a also divides m times b plus n times c. Whatever you want to choose for m, whatever you want to choose for n. If you choose m equals to n equals to 1, this means that b plus c. If you choose m equal to 1, n equals to minus 1, then this becomes b minus c. And if you choose different values, that they are also correct. Okay, so that is a very, very important rule I want you to remember. Of course, the main important rule is the sum and the difference. But if you want, and I want to solve this as an exercise, okay, prove this formally. Okay, exercise. So I think it's a very simple one, but it's good to know about these things. Okay, so Now let me give you another example. This is a better example. You need to be a little bit more creative here. So example, let A and B be integers such that we know this. We know that 13 divides A plus 3B. Show that 13 also divides 9A plus B. So these questions are a little bit harder. So I don't know anything about the numbers A and B, except I know that this combination is divisible by 13. I want to guarantee that if that is the case, this combination is also divisible by 13. Yes? So, for example, can you give an example for A and B which this one will work? For example, if I take A to be 1, B to be... no. If I take...
Yes, A can be 1 and B can be 4.
No. Yes. A 1, B 4, yes? This is one example, one of the examples. So, and then let us check this one. 9 times 1 is 9, B is 4, becomes 13. Yes? So that's divisible. So if that is true, this is also true. But let me cook up another example. For example, let me take A to be minus 1, B to be 9. Is that right? 9 times 3 is 27, plus negative 1 is 26. 26 is divisible by 13. So that is a pair of numbers. Let me check here as well. So what is happening? 9 times minus 1, which is minus 9. B is 9, so it becomes 0. And 0 is divisible by 30. That's also correct. Yes? So it doesn't matter. As far as you have this guaranteed, we want to show that this is also guaranteed, whatever A and B are. Okay? So how do you think that we should solve this problem? Let me give you a little bit of time so that you can have a chance to think a little bit about that yourself first. Okay, let me solve this one for you. This needs a little bit of experience. So let us. I start from there. I don't want to use the different rules to confuse you. I just use the definition, which you have to remember. So when you tell me this, I can conclude, if I want to, that there exists a Q in Z such that the right-hand side number, A plus 3B, is equal to the left-hand side multiplied by that Q. This is guaranteed by the assumption that you have provided for me. Of course, this might look a little bit tricky because there is no natural way, apparently, to go from this relation to that relation. So you see, 13 is the same 13, so in principle I shouldn't bother about this 13. The only thing that I need to bother are two things. I need a 9 with A, I don't have it. I don't need a 3 with B, I have it. Yes? So I need to somehow get rid of those things that I don't need and bring things that I need. So what is your suggestion? You shouldn't say that I don't know what to do. You know a lot of mathematics, you need to do it some trial and error to see how it works. So what is your suggestion here? For example, you need to concentrate for one piece. For example, let us concentrate. Let us concentrate first for 3. If I want to get rid of 3, what can I do? What are the natural things that you can do to get rid of that 3 for 3b? One way might be is to divide by 3. But division, I will not go for it. Why? Because I divide by 3, it becomes A over 3. This becomes B. This becomes 13 times Q over 3. Then I will start working with fractions, which is not very good in number theory, yes? You want to stick as much as we can to integers. So let us forget about dividing by 3. Okay? Okay. But let us concentrate on A. I want to make it 9a. Can I do that?
Yes.
It's much better because here you might say that why shouldn't I get rid of 3 first because of that reason. I'm not saying that this is wrong. Might be that's also a way. But the natural thing for me to do, I will start by multiplying by 9. Yes? So let us see how this will work. So then I will say that if this number is equal to that number, it is guaranteed that 9 times of this number is also equals to 9 times this number. Yes? But then I multiply 9 in. Unfortunately, when I multiply 9 in, it's inevitable. I have to multiply this one here as well. So unfortunately, the problem becomes even worse. So it becomes 27b. And then on the right-hand side, let us keep it in this way. I have a 9. I can multiply it by 13. But let us not get rid of 13 because I need 13. Just write it as 9 times 13 times q. If you want to, of course, you can multiply. Okay, then what? So I fixed this. It's good. Still, I haven't lost track of 13. That is also good, which I needed. The bad problem is that I have 27b. I want to get rid of that 27. But I told you that division is not a good option here. So there's only one thing left. You have 27b. You want to make it 1b. One way is to divide, which is not good. The other way is? The other way is? You cannot say that I don't know. You have 27 ice creams. You want to have only one ice cream. You eat 26 of them. Yes? Is that possible that you don't know what to do? Yes? So now I have 27 B's. I want to have only one B. So what should I do? Eat 26 of them. Yes? So it means that what should I do? I need to subtract 26B. Yes? So what happens? It becomes 9A plus 27B. I eat 26 of them. On the right hand side, I have to also eat that one, yes? So what I do on the left, to keep the equality the same, I have to do this one as well. Is that understandable?
Yes.
Is the equality understandable for you? I subtracted 26b. What was the motivation? The motivation because I want to have one single b. And then I will have 9 times 13 times q minus 26b. Then what? Yes?
26 is 13 times 2.
Thank you. So you need to factor a 13 out. So I can factor a 13 out. So what is left is 9 times q. What is left from here? 2b. That is important. You don't want to have the most beautiful quotient. What you care is that is integer. Yes? And that is your integer. Yes? Q was an integer. And b was also an integer in the problem. So do you agree that this combination is definitely an integer? 9 times q minus 2b. This also is an integer. And that is what I need. 9a plus b is an integer multiple of 13. Integer, I emphasize on this word. So I don't care what this looks like. I care if this is an integer or not. If that's integer, I am done. So this means that, can I conclude this? Yes, and that's done. Yes? So you need to be a little bit more creative in these kinds of problems. When the lesson ends, it doesn't matter. We end it here, okay? So, yes, let us end it there. Yeah, don't forget to follow the quizzes. This quiz was a little bit harder, but the people who answered actually did it good. I released the grades. And if you have questions, you can ask me, of course. So don't let the due date pass without solving them. Thank you very much.